Well, now we've talked about angular position. We can also start talking about angular velocity. Okay, it's not going to be very easy for me. If let's say I'm looking at a car that's driving in a circle and I want to describe the velocity, it's not going to be useful for me to talk about like v sub x and v sub y because every moment that this moves, v sub x changes and v sub y changes. So I don't want to have to keep updating it. But I still want to be able to describe how fast is this car moving as it makes its circle and how fast is it completing a circle. How long does it take to complete one circle and what is the rate that it's moving in its circle. So we're going to use the term angular velocity to measure that. The variable that we use is omega. It looks like a W. It's not a W. It's kind of like a curvy W. So that's called omega. It's not W, omega, and it measures angular velocity. This is a Greek letter. So similar to how velocity measures how fast your position changes, angular velocity measures how fast your angular position changes. So let's consider a car driving around in a circle in cruise control. And let's say at one moment I know it's at this angular position, theta initial. And then later, a few seconds later, whatever, it's at this angular position over here. So that's a different, there's delta, there's a theta final is this one. So I can just, if I want to know what's the angular velocity, I can figure out how long does it take to go from this angular position to this angular position. So my angular velocity is just going to be equal to delta theta, that's my change in my angular position, divided by delta t, that's just how long did it take me. So this definition here, though, I just want to remind you, this is only true for uniform circular motion, meaning this value is constant, meaning the object is rotating at a constant rate. Okay, if there's any type of acceleration where the speed is changing, this equation will not be true. Can we just pause for a second and remember everything we said before about uniform motion? So let's all think back, like this little guy here, he's thinking back. He's thinking, what was uniform motion? Uniform motion, that was when our acceleration was 0. And we had this expression that our displacement is equal to v times delta t. We also had this expression v equals delta x over delta t. These two equations are only true when v is constant. This equation here that I've showed behind the little thought bubble, that's only true for uniform circular motion when we're not accelerating. Okay, so say bye to that guy. Thank you for helping us remember. This equation is only true for uniform circular motion. Uniform circular motion means that your angular velocity is constant. Okay. What units do we have for angular velocity? Well, our angular displacement would be in units of radians. Our change in time would be units of seconds. So our units that we're going to use for angular velocity are radians per second. So it's telling you how many radians of a circle are you moving through each second. That's what angular velocity measures. Now, since we're not that comfortable with radians, it might be tricky to kind of look at this radians per second and have that make sense to you and just think, oh yes, I understand what angular velocity is. It's measured in radians per second. But another set of units for angular velocity makes it make a little more sense. One set of units we could use is revolutions per second. So angular velocity can also be measured in revolutions per second, and I think that makes it make a lot more sense. Based on how long it took you to go from here to here, we could describe your angular velocity as a certain number of revolutions per second. And you can also describe it in terms of revolutions per minute, which has special units RPM, because that's a term that we use a lot to describe many different things. RPM, revolutions per minute. So I hope that thinking of angular velocity in terms of these units might help it make a little more sense when we're describing how fast is it completing its circle. Just like when we dealt with like our velocity in the x direction or our velocity in the y direction, we always wanted to make sure knew whether we were talking about, is the velocity in the positive x direction or the negative x direction, where we said to the right was positive x and to the left was negative x. So we need to also be careful about our signs here. So if I have an object that's moving in a circle, if that object is moving counterclockwise, we're going to consider that the angular velocity is positive. That's just how we define things. So something moving in the counterclockwise direction as it makes its circle is a positive angular velocity. If the object is moving clockwise, we're going to consider that negative. So these are just things we're going to have to remember for now. And when we're going to see this a lot as we start talking about objects that are moving in a circle, but it's nice to kind of make an analogy between the kinematic variables that we're learning, these kinematic variables for objects that are moving in a circle, and how they're analogous to the kinematic variables for objects that are moving in a straight line. So the relationship between omega, our angular velocity, and theta, our angular position, is just like the relationship between what we've seen before for v and x. Okay, so let's just remember this was for uniform motion only. We said delta x equals v delta t. If there was not uniform motion, if the object was accelerating, we had to use one of those other more complicated kinematic equations. Well, the same thing is going to be true when an object is moving in circular motion. If we're talking about uniform circular motion, which means omega is constant, which means nothing is speeding up or slowing down. There's no speeding up. The speed is the same. Nothing is starting to spin faster and faster and faster and faster. That's not happening. That would be uniform circular motion where omega is constant. Then this simple equation can help us relate our angular displacement to our angular velocity. Other relationships that are the same, if we had a theta versus time graph, omega can be found from the slope. Just like if we had an x versus t graph, v could be found from the slope. That's what we saw before. And if we have an omega versus t graph, delta theta is the area underneath the graph. Just like when we had a v versus t graph, delta x was the area underneath the graph. Okay, so keeping in mind these relationships, these are kind of the calculus relationships. Try to find the match. This is my angular velocity as a function of time. And I want to find the match, which one of these theta as a function of time matches it. So take some time and try to work through it. Well, what I want is something, where this value here should be the slope of the first part of this graph. So I see something that's constant and positive. So I want to choose a graph that has something constant and positive slope in the beginning. Well, this has a constant positive slope. And then after that, this has a negative constant value. That means I want the slope of my angular position graph to have a negative constant slope. So there's that. So it's going to be B. Okay, so here we have this train driving around a circular track. The track has a radius r. The period of the train's circular motion is big T. Now remember what period means. That's how many seconds it takes to go around once. Based on these two variables, I want you to tell me what is the angular velocity, omega, of the train. So press pause, take some time to work through this, and then press play when you want to go through it with me. So remember, omega is measured in radians per second, and if it's taking me big capital T number of seconds to go around the circle once, how many radians do I go through? Well, I go through 2 pi radians in a time equal to big T, and omega is equal to how many radians you go through and how long it takes you to do that. So that's going to be D. 2 pi radians in big T seconds. That's another way to relate, to define what your angular velocity is. It's how long does it take you. So big T is how long it takes you to go around once. And when you go around once, you go through 2 pi radians.